Well, sometimes it pays to actually talk to people before you expend a lot of time. But actually, I wanted to see how much of this I could figure out without it. But Dave contacted me about some other things, and I mentioned to him that I started this and that I didn't have a service manual and it was kicking my butt. And he basically said, "Don't you remember I sent you a service manual? I found somebody that had one and I got it for you." And I'm like, "No." So he's like, "I'll resend it to you." So he sent it. Lo and behold. So I looked through it, and wow, this thing is a crazy design. I don't think there's anything else out there designed like this. This is probably, and I don't know, maybe NEC in some of their other amps of this era used some of this technology, but it's pretty crazy. Some of it I really scratch my head why they do it, but other things, maybe it's going to be pretty cool. So here's your, and I had access to this from that website, that Vintage Knob website. Yes, the Vintage Knob. Okay. Anyhow, you can see that if it's rated at 70 watts into 8 ohms and 140 into 4 ohms, where it can truly give you double power, it means this must be a really high power amp. DC servo circuit. Well, remember I said that some of these op amps are probably being used as servos to hold this thing into, hold the DC offset and everything stable. This does have that. Plus, it has some other things that it uses servos for. Pretty crazy design. So let's look at some of the schematics. Now, the first thing I'm noticing is when I read through this, the EQ amp and the flat amp, just like we were seeing looking at this, they're the same circuit. The only thing they did was change component values to change the gain of the circuit. So they're using the same basic circuit for the phono, and then they're adding the equalization for the RIAA. So there's a filter network in there. And in the flat amp, it has much lower gain, and of course it's a straight through. It doesn't have any kind of attenuation or filter circuit for the EQ, for the phono equalization. Other than that, very similar circuitry. Some pretty strange things going on here. So you have a cascaded input pair with gain. So you have a JFET input, and that's what those JFETs are for. Now, remember I said I thought this was kind of like what Carver was doing, where they use this to kind of shut down the inputs so you don't get, noise when you're switching. But no, actually it's a JFET input, and then it's cascaded with that monolithic, 2SC 2291 transistors. So this is actually a voltage amplifier as well as, and then it goes through this stage with a current mirror and a current source. And well, this isn't the current mirror. The current mirror is further down the line. But it goes from here through a current mirror into the input pair, which also has a constant current supply. And they're using those JFETs as the constant current supplies. Instead of using the transistor with the diode and so forth, they're using just the simple JFET current sources. So you have your cascaded input pair. So right at the input, you start with gain. Then you go through your differential input pair like this, where your feedback and your input signal are combined, and that's, of course, does not have gain. So it's kind of weird. They do gain before this. A little different than what we're used to seeing sometimes. And then you have a current mirror, which doesn't really show. If you look at the real schematic, it's a little bit different how they draw it. But basically, your current mirror is in here, and here's your input pair. and then they turn it into they keep calling it a SEEP. If any of you know what this stands for, this acronym, SEEP, I've only seen SEPP, which is single-ended push-pull. That's pretty much what they're doing here, but I don't know what that stands for. And nowhere in this manual does it talk about what that means. They just assume that you know what that is. See, it shows a simplified SEEP type. I don't know, whatever. So go into this. You have your output, and then you have these servos that they're using for the negative feedback circuit. It's pretty interesting. And they're showing you a block diagram of kind of what they're doing. This thing's got a lot of gain in it. And then in this one, they're showing they're showing you the equalization circuit, which doesn't exist on the flat amplifier. It's the same thing, just doesn't have the filter circuit, or the equalization circuit, I should say. And there's your DC servo. There's a block diagram of how it works. This is basically adjusting your frequency roll-off. So this is allowing the feedback to kind of roll off the high and low frequencies, along with, so the feedback is kind of variable based on frequency. And then here's the big picture, not including the outputs and drivers. And you can see right there, they're saying that A is your cascade input with gain, and then your differential circuit is here, and then point C is the current mirror. And you can see they kind of draw it a little different, so it makes a little more sense how it works. There's your servo down there for feedback, and then it goes into this is kind of your bias circuit right here. That would be your bias, and going into your single and your push-pull. So this is your phase splitter, and then it goes out to your outputs, and they kind of show that here. And it's a Darlington configured output. So you have this. They have a triple Darlington. And then the outputs are actually, they're not showing the second one, but there's 4 transistors here and here. Interesting. Very interesting how this all works. So, and then you go into the main amplifiers, what they're calling the main amp P, which is power. So there is a main amp V, which is your voltage. What do they call it? Where's that? Where does it say that? The schematics are pretty involved here. They're very complete. Yeah, main amp V for voltage amplifier, and then this is power amplification. So this is for your current. These are the outputs. And then you just have this transistor here, which is what goes to your protect circuit. So that's for like your overload protect and DC offset measurement. UPC 1237, so your protect circuit is pretty basic. That's pretty normal. And now's where it gets weird. Here's the reserve supply they're talking about, and I really don't understand why they had to do it this way, but I don't know. Maybe it's because they can use smaller transformers to get more power. If you wanted to do this with a single transformer, it'd have to be bigger, but I would think one big transformer would still cost the same or less than 2 little ones and all this mess. But you see all these steering diodes? So you have your primary power, which is this first winding. And not only does it go through a bridge rectifier to give you your positive and negative voltage, they're not showing they are showing your capacitors here. But they go through these steering diodes, for your positive and your negative. And the reason they're doing that is they're connecting in a second power supply. And if you ever tried to put these bridge rectifiers in parallel, you'll get a short and the thing will die. It'll short out in short order, no pun intended. And so they use this diode here as a steering diode, and these as well. And you can see this pair of capacitors just kind of stays charged fully all the time. And then if the ripple voltage droops below this voltage, then it will be higher, and this diode will break down and it will conduct and it will bring that back up. So in theory, what it's supposed to do is supposed to give you a lower ripple. So you can see with just a single power supply, conventional, you have that normal ripple that you see there in the dark, the straight line. The dotted line shows what it's like, how much it's reduced by using this little system here. Now again, you could still do that by having a bigger transformer with bigger windings, lower impedance, and higher current capacity, and do away with all this extra crap. But again, hats off to them for trying something different and new. Okay, so here's the integrated circuits. Here's the wiring diagrams. So we should be able now, and see, it's got everything in here. I should be able to trace where we're losing it. Okay, so it is now the end of the video, and I was in the process of editing this epically long video, which I'm probably going to split into 2 parts just to make it easier to upload. And I got to the point where I started describing the schematics and so forth, and realized that there was quite a few things I glossed over, and I think I should probably go back and be a little more detailed. So I'm going to just do a rundown of the basics of how this thing works. I'm going to kind of weave in a little bit of those previous clips with this, and I'm going to kind of mix them together and hopefully give you a good idea of how this thing works. So what I was working on, and what was the biggest problem, were these current sources here. And you can see them. So this is the equalization amplifier. It's the same general circuit that you see on the main amplifier here. And this is the one we were actually troubleshooting. They're doing the same thing. There's 3 of everything. So there's 1 power supply for the EQ amp, 1 power supply for the flat amp, and they're the same circuit, just different boards, and then a power supply for the main amp. And then there's a big power supply for the outputs. We'll talk about that later. So let's first look at what's happening here. So there are 2 op amps on each board, and they're MC 4558s or whatever 45. They're 4558s. They're a decent choice for this because this is your voltage regulation. This is actually just a variable power supply, and you're just using this pot to adjust the voltage. And it's just, you have a bigger voltage going in, and then you adjust it and you drop some voltage here and you have a smaller voltage coming out. And these pass transistors are what cause that. It converts some of the voltage into heat, if that makes sense. Which is why those heat sinks get really hot. They're supposed to, because this is the way this thing was designed. It's not really very efficient. So this is all a feedback system. One's for the positive voltage, one's for the negative voltage, and other than that, they're mirror images of one another. So you could kind of cut this off right here, and from here up is the positive supply, and from here down is the negative supply. And in order to power these chips, these 4558s, they're powering them with a plus and minus 15 volts. So if you look, it says IC 4401 and IC 4402, all right, and pin 8 and pin 4. So you can see it goes pin 8 and pin 4. So this is all one chip. There's two op amps in this one chip. All right, if that makes sense. So what they're doing, which doesn't make much sense to me, is they're taking positive 70 volts, and if you look, you have 3, count them, 1, 2, 3 Zener diodes in series, Okay, so it's a shunt regulator. And then in order, because you're dropping such a huge amount of voltage to get 70 volts down to 15, there would be excessive current in here if you did that. So they tried to curtail that a little bit by putting this constant current supply in here. So what that's going to do is it's going to limit how much current can flow through these Zener diodes, and conversely it's going to limit how much current you can deliver to the integrated circuit, which doesn't take very much. It's just milliamps all you need to run this chip. So in order to do that, you're going to have less current flowing through these Zener diodes, so they're not going to get as hot. So you can put a 1/2 watt Zener in there and it won't hurt it. And since you're spreading it across 3 diodes, it can take it. But you're doing it at the expense of this current source, which is why they have 3 of them in parallel. And even at that, if you take, and I'll do the math right in front of you here, you take 70 volts, all right, and you go minus 12 for this first 12 volt Zener, minus another 12 for the second Zener diode, and then minus 15 volts, you have 31 volts being dropped across these little JFETs. Now, we determined that there's about 12 milliamps there, so you times that by 0.012, and you have almost, not quite, you got 372 milliamps, so it's just under a 1/2 amp of current, or 1/2 watt, I'm sorry, of current being dissipated in those little tiny JFETs. They're really not designed for that. The other problem is with 31 volts dropped across there, those original JFETs were 2SK104s, and the maximum voltage for a 2SK104 is 30 volts. So you're putting 31 volts across a 30 volt FET, and I question these. I wonder if these were replaced at some time, but every single one of them were K104s. But if you look in the schematic, they're saying 2SK105. Do you see that there? Let me move this, 2SK105. But clearly they had 2SK104s. See it? So that's why all of these failed. They had too much voltage. And I could not find a 60, there are some 60 volt JFETs out there, but they're hard to find, and when you do get them, they're very expensive. A 60 volt JFET, most of the ones I was finding from legitimate dealers, was upwards of $6 or $7 a piece. And remember, there's 3, 6, 9, 12, 15, 18, and then 19, 20, 21, 22 of them just in this one power supply. And then there's 22 more of them here, another 22 more in the flat amp. So there's 66 of these daggone things. You times that by $5 or $6, $7 a piece. There's no way I'm going to spend that money on this amp. And it's just not plausible to, to me it's not a good idea to do this. Now, once you do that, they did the same thing over here. So you have this amp, or this power amp section here, and you have the right channel here, which is just this over again. So you could see 2 more of those shunt regulators to drive 2 more of these ICs. So you got one on this channel, you have another one on this channel. All this circuitry just to provide the 15 volts for an IC. Why wouldn't you just make a normal power supply like everybody else does that can handle more current, and just use a regular pass transistor linear regulator? I don't know. And again, with this is a very highly regulated, has this op amp. It has a comparator circuit, so you have your 12 volts or 1.2 volts here and 1.2 volts here. You adjust this so that these two reference values match, and then you should get, they're saying I think 50 volts here, but the book tells you to set it for 54 volts. So you have plus and minus 54 dropping down from 70. So again, whatever amount of current this whole thing draws minus the voltage drop, with that voltage drop across here, you times that current times the voltage drop. That's how much heat, how many watts in heat this thing's going to have to dissipate. Again, these get really, really hot, and by design. Bad design. I don't think it's a good design. Now, if you take all of that out of there and look at this, and if we ignore this servo in the feedback circuit for a minute, this is a very common, complementary power amp, push-pull power amp design from the era. You have an input pair. Now, one of the differences is here, you have the current mirror and you have the current source and you have the, the input pair. But a lot of times, usually this input pair is for impedance matching, and you won't have gain in this stage to keep it quiet because you don't want to amplify any noise at the input here. But this stage actually has gain, and then it's just gain all the way through. So I could see how this amp could possibly be noisy, especially if any of these components these transistors start to get tired or something. In addition, you have a op amp that's a 4558. It really isn't designed for audio purposes. Right in the audio range, the slew rate sucks, and that could definitely affect how this feedback circuit works. And now I don't know if they did this because back when this was designed, because this is an old design, it's an old amp, this might have been one of the better ones out there, but I believe there were better quality op amps at the time, but they were probably really expensive, and they did this to cut costs. You could probably remove all of these and replace them with like NE 5532s, or some of the even higher end ones, some of the OPA series or something. Even a TLO72 would probably be better than this 4558. Would be an improvement over these. So that probably would help. So if any of you have one of these and want to improve it, swap this out first and foremost. Do a recap on it. Check all of these input devices here and make sure they're good, because if they're starting to get noisy or leaky at all, just expect expect this to be a noisy circuit. So what I did here was I removed these JFETs and I replaced them with 3 7.5K resistors in parallel, which gives you about a 2.5K resistor, and they're 1 watt each, so there's at 3 watts. They still get hot. Even though it's 3 watts worth of resistors, they get hot because they have to. They're dissipating, almost half a watt of power. They're going to get hot, especially since they're small body resistors. If I got bigger ones yet, they'd stick off the board, but they'd run a little cooler. And this thing came right up and worked perfectly. That's what ended up fixing all this. The other weird thing is this power supply here. Look at all these diodes in here. So you have your 2 transformers coming in here, and you have one winding off of one transformer and one winding off the other transformer, or your 2 windings. Same here, 2 more windings. So this is P1, P510, P513. So anyway, what they're doing is they're full wave rectifying, through a bridge, the 2 windings, and they're both the same voltage. But you can't just tie them in parallel because they'll fight one another and this thing will just blow fuses. So what they do is they put these extra steering diodes in here. Notice there's 4 of them. So look at all the voltage drops. Each one of these diodes has a forward voltage drop of upwards of 1 volt when you start putting this kind of current through them. Look at all the drops you have. And then they're using these capacitors to kind of fill in the ripple. That's what's giving that intertwined, ripple recovery, is this design. But in exchange, you have to add all these extra diode drops, which diodes have switching noise unless they're very, very high-end diodes. And these ones look to be, they're those ones that look like transistors, but I don't think they're fast recovery hex-fred diodes. I think they're still pretty much standard diodes, and they're not bypassed by any kind of little capacitor. So these, you got a lot of switching noise here. So again, just an unnecessary design, in my opinion, where you could have put a larger transformer with a heavier winding. It's toroidal. They're very good at recovery, from high current, and just put a stiffer, you put the same number of capacitors, put them all in parallel. That would give you really low ESR on your cap bank. And Bob's your uncle. This thing would work great. So that gives you an idea. I mean, when you look at it, other than the servos and these weird power supplies, this is just a standard amplifier from the 1970s, late 70s, early 80s era. They just did some weird power supply things, and this was an early version of amp with these servo feedbacks. And in the EQ amp, they're actually putting in your network for the RIAA, for your equalization. And then in the flat amp, they have the same circuit, but they take these, they don't have all this network. It's a different network in there that doesn't have the curve built into it. But other than that, it's a servo. If you go back and look at my Adcom GFA 585 series, it uses these, but they're much better quality op amps and a lot better execution of the circuit design. And that's one of the cleanest, most powerful amps I own right now. So it can be done with this, but not this way. So I hope that kind of clears up how this thing works. Armed with that knowledge, neither channel is working. So I've got my needle stuck on the record here on this. We measured 70 volts here before we had the service manual. We need to see if we have the 50, plus and minus 50 here. So we need to find a place to measure that. And it appears that it should be pretty easy. There's a lot of places here we should be able to pick it up. So let me, first of all, if I go on these current sources, I should be able to read between here and ground and see 50 volts. And if you remember, I was not seeing 50 volts. I was only seeing, a couple of volts on these. So what's up with that? Let's find out. Okay, so these two resistors, these pots here, are going to be these for setting your plus and minus 50 volts. And there's going to be, it's kind of weird that I only see one. Okay, so there is only one set for both channels. So it feeds both channels. If you look, it comes off of here, it goes down to the other channel. So there's only one, and that's this center point. So those are for your voltage amplification power supply. You then have two other pots. There's one here, and then there'll be one on this channel. That's for your bias. And this just looks like just a VBE multiplier circuit. And the pots for that are down in here. That you can't see them from where you're at, but they're just straight down there. So let's see if there is a procedure for adjusting that. And indeed, there are. So it appears that there's an adjustment for the EQ and flat amp, and in fact, you can just see up here, there's a pot there and a pot there. And I'm not going to mess with those because that seems to be working fine. So let's look at the main amplifier. Adjust V4401, so that would be this one, and V4402 for this is the positive And this is, wait, I'm sorry, this is the positive and negative voltage. So I'm going to mark that there so we know. Hold on. Okay, it says to adjust these pots, and there's a J418 and a J423, and sure enough, you have to really kind of look up underneath there. But there's two little loops here. They're just jumpers with the wires just kind of looped up off the board. There's one there. Here's the other one here. And you just put your meter on there. And I'm not going to do it with it on. I'll turn it on after I do this. But I'll hook this in here like so. And I'll see if we get 55 volts is what they're saying. So I'm going to turn this down. And we'll just see what happens. Okay. Power on. I get nothing. That's the same voltage I was getting on those JFETs. How about that? Well, that would explain a lot now, wouldn't it? Let's see if I can get this hook off of here. And I'm just going to touch this other test point and see if there's the other side. It's 2 volts, which was what I was reading on those current sources. So for some reason, I'm not getting anything out of that power supply. What the heck is going on? So I should see on the collector of this these two transistors, I should see positive and negative 70 volts, right? And I don't. The unfortunate thing is you got all this in the way. So I'm going to have to take that cover off and see if I can reach that. This is a horrible, horrible design to work on, let me tell you. It is not designed to troubleshoot. Okay. I've got that cover off. I should be able to get down in here. I'll turn this on. I've disconnected speakers and all that stuff because we don't need that. I'm going to try to get on this pass transistor without shorting it out. And the collector should be the center terminal. And let's see where there's our schematics right here. So right there's our collectors on each side. And I just need to see if collector will be the middle terminal. I just got to be really, really careful in here. And see what I get. Let's see. I should really I'm going to put a piece of heat shrink over here. Hold on. Okay, so they make those little plastic things that snap over the end that lets just the tip stick out, but they're so wide that they get in the way. So I'm much prefer to just do this. Okay, let's see if we can get in here without shorting things out. Yeah, 1.9 volts. There is nothing going into these. But the strange thing is, it appears that there's voltage out there. I mean, if I look at the voltage coming into the wires here, there's negative 64. It's not 70 when I plug that in. So something is really loading that down. So where are we having problems here? Okay, I have the board back out, and I have this wire stretched across here and plugged into the amp over there. And if I turn this on and I knock over this light, so pins 8 and 4 are your positive and negative supplies on this regulator IC, this 4558 op amp. I've got negative 4.6, positive 6. That's completely whacked out. And if I look at the output of the one channel, it's nothing. I believe that's the output. No, the output is here, pin 1. You can see it's jumping all over the place. And if I look at the output of the other side, it's all messed up. This chip may possibly be bad. Unfortunately, I don't know where the voltages are coming from for this, so I'm going to have to look at that for the power supplies, but they're definitely not right. I don't think this thing is running on, I don't think it's supposed to run on the plus and minus 5. I think they have it set to run on plus and minus 15, which is what these are. These are supposedly, I would say these are the voltages that feed this. They don't really show it anywhere, but, you know, I just have to think. And they're saying 4 and 8. Yeah, IC 1402. There it is, 4 and 8. So yeah, these are our feeds right here. And this would be TR 4413, 4419. So I wonder if these were bad, if you remember. I'm wondering if the ones I replaced are not correct, possibly. I don't know. I'm going to have to check this. Okay, now I see. So that is not correct. These are the ones I replaced here, which are these ones here and here. And those feed 401 and 402, not 4401. 401 and 402 are these ones down here for the servo. They don't really matter at this moment in time. These ones are original. They didn't read bad. I did not replace them. So we're not getting the plus and minus 15 volts here. There's something wrong. So the fact that they're both bad leads me to think that, again, we have a shorted integrated circuit. So I'm going to pull this chip, and then I'm going to see if my 15 volts comes back. Okay, I have the chip pulled out, and I'm on D4401 cathode, which is right here. See that? And this should be plus 15 volts if I go here. So let's go right on there, turn it on. 15 right on the money. Look at that. All right, and then let me go to what do I want? 4402, the anode. 4402 anode right here. Turn on. Ha! Negative 15 right on the button. How about that? I think we have a bad chip. Okay, here's the story. These 2SK 105s, there are 12 of them. There's 3 here, 3 here, 3 here, 3 here, 3 here, 3 here. So 3, 6, 9, 12, 15, 18. Okay? And not only are there's those, then there's one more here. So that's 19, 20, 21. There's 21 of these 2SK 105s. The problem is these ones here where they have 3 of them ganged together, they were bad as we measured them. They're $7 a piece, and if you can find them. And you can't be guaranteed that those are even good ones or real ones. That's just a lot of money to put into an amp that I don't think is worth it. So doing a little bit of math, for instance, if we look here, these are all for making, all these are doing is making a 15 volt power supply, and you're just dropping some voltage across these right here and right here. And so if you, let's say you have positive and negative 50 volts, so you really have like 50 volts from here to the center. If you take the 50 volts minus 15, you have 35 volts. So you're dropping 35 volts across here. We know that 3 of these in parallel is going to be somewhere around 12 milliamps because we measured them at 4 milliamps each, and it tracked about 12. Long story short, we need about 2.5 K would be a good resistance to make a resistor current limiter in here. Now that's going to draw somewhere, you're going to dissipate somewhere around a half a watt, which is going to make those get really warm. So what I did was I took three 7.5K resistors, and you can see them right here. And I just used a 7.5K resistor at 1 watt, and these are metal film. I just put them in place of those FETs, those JFETs. And guess what? When I did that, let's turn this on and see what happens. Remember, here's our test point that we need to get our plus and minus, would they say 50 volts or 54, according to the, I'll have to get the instructions back out. But turning this on, if I grab a ground here and I move you over so you can kind of see what I'm doing. Yeah, this is real janky how I got this set up, but test point 1, look at that, minus 47, plus 54. And probably if I adjust this, I should be able to move this pot. No, I can't because my fingers are clogged up with all this. But I should be able to adjust this. So like, I'll move this a little bit. Go here. 44, so that's the wrong way, so I want to go that way. 51, see that? So it works. It's fixed. So essentially what was wrong on here was those JFETs, a whole bunch of them were bad. They're very expensive and hard to find. The J112s that I tried to replace this with, I think they were J112s or 2N5458, whatever. Even though they worked on the breadboard, they did not work in circuit. So these resistors are a good and cheap alternative. And I'm just feeling these, they're getting pretty warm. So I may have to up that a little bit to a little higher wattage resistors. But basically the concept worked. And this is going to be fine. These are running way cooler now. And I think this is pretty much what we're going to need. Okay, we're all back together now. And I'm hooking up my meter. And we're going to go back and do our test of these two test points. What are they called? J418 and 423. And these are, again, these had 0 volts. And it was because those current sources were bad. So now they're replaced with the resistors, which are going to get warm. And I probably should have a little bit larger sized resistors, but they're well within their rating. It won't hurt the resistors. It's just they're going to give off heat. And we'll see how much heat after a while. You know, if it's too bad, we'll increase those, but I'll have to order those. But I'm not ordering those JFETs because they're just so expensive. It's just not worth it to this amp, to me at least. If somebody else wants to unsolder my resistors and go buy all those JFETs, or they have them and want to put them in, that's great. One thing I found is if you look at the 2SK104s, which these are actually 2SK104s that were in there, the originals. But the schematic calls for 2SK105, and the main difference is these are a 30 volt component, and there's actually 32 volts being dropped across those JFETs when they're operating because of the function of those Zener diodes in the schematic. So what is Tony talking about here? Well, let me see if I can find the schematic, and I'll show you what I'm talking about. So if you do the math, you have a 12 volt Zener diode here, and you have a 12 volt Zener diode here, and you have a 15 volt Zener diode here. So you have 24 volts and then around 40 volts, right? So actually, what, 39 volts, okay? So there's 39 volts, and you have a 70 volt feed going into it. So the difference between 70 volts and 39 volts is going to be a lot more than 30 volts, right? So that the actual potential that you're going to see, the difference across here, is going to be greater than the maximum, the absolute maximum rating of the 2SK104. Now the schematic, if you look, says that they should be 2SK105s, and they are not. They're 104s. So I think somebody replaced these once before. The 105s actually are a 60 volt component. That's the main difference between a 2SK104 and a 105. So they had to fail, just like the ones that I put in, which were similar to a 2SK104, they were also, they had failed very quickly. So that's your problem. Again, finding a 60 volt JFET like that is rare. They're very expensive when you get, there are a few for sale like at Mauser and DigiKey. They're not the 2SK ones, but they're similar. They're $6 or $7 a piece, times however many's in here. What is there, 12? No, I'm not spending that on this for JFETs. So let's connect to our test point. This should have voltage now. Let's flip this on. And there it is, 54 volts. And they actually want, in the manual, they want it to be 55, plus and minus 55. So that should be easy enough to adjust. Let's see if I can get 55. There's 55 there. Let's go to the other side now and see what we get. That's 52 almost. So let's get that to 55. And there we go. So that's pretty close. I don't think that little bit's going to matter. Okay, so we have our plus and minus 55. Do we have... So really, what were all those things doing in the first place, you might ask? All these things do is limit the current to these 15 volt power supplies. So you have a plus and minus 15 volt power supply, and its only thing is to power this one op amp. Then you have two other circuits that take the 55 volts or whatever that is and step it down to plus and minus 15. One is for the right channel, one is for the left channel, and it's for driving the servo op amp on there. And because these were all bad, we weren't getting plus and minus 15 volts to our op amps, so none of the bias circuits or anything, or the feedback loops would work. So the amplifier was pretty much dead. So now that that's all good, everything should be working fine now. So I think the next thing to do is let's connect a signal source back up and see if it works. Okay, I have my signal source connected to the auxiliary input. I'm looking right at the speaker terminals. There's no load on it, so we're just looking at open circuit, with no load. That way, we're not putting any heavy load onto the power supply yet. I just want to see the output get through there. And I'm looking at both the left and the right channels. And the blue lead is connected to left channel, and the yellow lead is connected to the right channel, and I have them over top of one another. And let me see. I'm going to go to 1 volt per division. All right, let's turn it on. Okay, protect pulled in, and look, we have about we still have a bad DC offset on the one channel, on the left channel. But, let's see. But we're getting, other than that offset, we're getting a clean signal out. That looks good. So, there is definitely a DC offset. I'm going to have to find out what's going on there, and that could very well be an adjustment in the flat amplifier, because you actually have to balance that. So that may not be a problem. That might just be an alignment issue. But the amplifier's working. We fixed it. Wonderful. Okay, this is absolutely heinous trying to get to this. So what they're doing is, first of all, this looks absolutely nothing like this circuit board. Take a look at this. take a look at the circuit board. There is no semblance, there's no resemblance between either at all. But I did figure out from the schematic that essentially what they want us to do is they want us to look at the output of the preamp. So right there, 380 R381, see the output, and down here R382. And they want you to just set the pot till there's no offset. This is your DC offset, so they want 0 volts on there. And you can see right now we have negative 54 volts, and there's really no way to get an alignment tool on this one or on the EQ amp, because it's the same adjustment on that too. So I'm just going to try to turn it with my fingers, and of course it has glue on it. This amp, I don't know, not my thing. And it looks like this thing has a little delay. There we go. Okay. And looking at the oscilloscope now, it's really hard to adjust with your fingers. I should have left well enough alone. I think that's close enough. 0.1 millivolt. And you can see now the offset is gone on the scope. See that? Okay. Now I'm supposed to move it to the other side, and that resistor is absolutely freaking buried. I don't know if you can see this or not, but so if I come off of here, the other resistor is all the way down underneath this connector. I mean, it's like daggone near impossible to get to. But really, you can also check it where this connector comes out down here. So I might be able to disconnect the plug from there and hook my probe onto that, because getting on that resistor is going to be next to impossible. Okay, as you can see, or maybe can't see, I have the connector right. I just pulled the connector and I'm right on the pin. So let's see if I can get this to adjust. And the pot is way down in here, but at least it's facing upwards, so I can actually get to that if I have the correct alignment tool. If you're not an experienced service person on these, you're going to hate this thing working on it, because it is a little bit challenging. So let's see here. This should get down in there. I don't even know if I'm on the right connector or not, but let's turn this back on. And yep, I am on the correct one. And it's just about the same amount off. So let me rotate this. If I can get it. Oh, they covered it with glue. Oh no, it's facing the wrong way. How are we supposed to turn that? I have no idea how we're supposed to turn that. Okay, let me get in there and figure out what I have to do. Okay, I don't know if you can see it, but you see how this pot is facing out? This one is down here, right where my finger is, and it's facing out also. How are you supposed to get to that? Nice. Really nice. Well, I hope I'm not shorting anything out, but this is the only way I can get to this. If it blows up, well, I don't have to worry about it anymore, I guess. Okay, there's that one. Now how is that I just moved it? I didn't even touch the pot. Literally, I never touched the pot. And it was reading high. Now it's not. I don't know. All right, so let's grab this thing here. See if I can get a little closer. course, this isn't going to work. Just jam this screwdriver in there. I don't care. Put the glue. There. There it is. Okay. All right, so we have that one. And we have this one. And it's drifted a wee little bit. So I'll touch it up. Just right on that edge. Okay. Close enough. I mean, I think if we're within a millivolt or so, we'll be good. Now this one is even worse. I see the connector for the first one, and luckily it's good. And the other one, well, I can't get to it. Gonna have to figure out how to get down in there to get to it. Okay, so those little coaxes come from down there where you can't get to them, and they come up and they come through here and they go to here. So I can just jam the probe into there and I can measure the offset, and that one is 0.3 millivolts and this one is 0.3 millivolts. So luckily we don't have to touch that one. The only one that was out was on the flat amplifier. So we got that, and it's good. So thankfully, because I'll tell you what, I can get to this top one. That bottom one would be a real bear to get to. I don't know who designed this amp, but they should have been immediately fired as soon as that this thing came off the drawing board. All right, let me put it back together and we'll see if this thing works now. Okay, I do not have direct replacements for all these things, but what I was able to do is take this little green booty off of this burned out bulb, and I found a replacement LED that I can slide this over and perhaps wedge this in there somehow into the faceplate. Let's see where it's at, where it is. And it kind of goes in behind here somehow, so I might be able to get that to mount in here some way. So I'm going to do that. We'll see what we can make of it. And for this jack, I had almost this, but not quite. So I'm going to remove this board, and I'm just going to install this connector here. And it'll fit right in this mount. So that should get me where I want to be. Who knows? Who knows? Okay, so we have this silly thing all back together, and the faceplate and the knobs and the covers are all back on. And what we're going to do is we're just going to do our couple of tests to make sure it's performing okay. I'm going to do, the 1 kilohertz thing, and I'm only going to put 150 millivolts RMS because supposedly that should give us enough gain to get full power out of here. So we're going to try that. Let's get the scope ready, and I'll turn the amp on, get it warmed up, and then I will be right back. Okay, the amplifier is turned on, signal generator's on, and we're connected across an 8 ohm dummy load. And we're going to read the output and just see what we get. So 1 kilohertz, and I'm at 20 volts per division on the scope, so let's see where it clips off at. Right about there, see the clipping? Right about there. And that is going to be about 25, right around 25 volts. Let's say 25. It's a little above 25, but that gives us 78 and a quarter, or 78 and an eighth volts, 78.125. So for 70 volt amplifier, you're getting 78 watt, or 70 watt amplifier, you're getting 78 watts at clipping. And that sounds pretty reasonable to me into a dummy load. Okay, I'm going to try the sweep test now and just see how flat this thing is. We're going to go from 20 hertz to 10 hertz, I'm sorry, up to 20 kilohertz. We'll just see if we stay in the lines here. See if it breathes. And you can see it is shrinking a little bit. As we get up close to 20 kilohertz, there's a little bit of roll off on the high end. Not much, but a tiny little bit. Okay. So that's good. Okay, let's take a look at 20 hertz. And my scope is kind of sluggish because of the refresh rate. You can see it's hanging in there pretty good. Let's go check clipping. Make sure we don't trip our protect circuit. And you can see that's pretty normal. And do you notice how you don't get that fluttering at the top at clipping? That is what that power supply is supposed to be all about. If you notice, when on amplifiers that don't have really solid power supplies, the voltage drop, or the voltage droop as they call it, on the power transformer will cause that little 60 hertz flutter. So like right at the top of the clipping, when you're up here, let's see, right there, that flat top would start to kind of flutter, and that's because you're actually kind of starving the amp for power, because the transformer is kind of starting to run out of current. It can't keep up with the current that it needs for the capacitors. So it does do its job, so that's what it was designed for. Now, could you do the same thing with just a larger power transformer? Absolutely. So this is kind of a Rube Goldberg method of doing it, but it works. And you can see that it's pretty solid. I'm still at 20 hertz, but I've switched down to a 4 ohm load. By all the rules, I should be able to get double the power. So I should still get the same voltage, maximum voltage output. So let's see, we should still be able to get that 25 volts before it, clips. So let's see where we are. And you're starting to get a little bit of parasitic oscillation. You see that? And that's probably has to do with the servo circuit. Right around 20. And it clips. It's clipping a little early, but it was on an 8 ohm load also. Full disclosure. Let's go to 1 kilohertz. And let's speed this up a little bit. All right. Okay. And let's see what it wants to do. And see, it does not oscillate there. And it's about the same. It's clipping a little bit, about 23 volts. So you're getting some pretty massive wattage into 4 ohms. That's pretty good. Okay, here's all the marbles. We're at 20 kilohertz into 4 ohms. All right. And let's see what we get. You can see there's distortion a little bit. But you can see again, a little bit of oscillation, not bad. And again, it's clipping at about 22.7 volts, which is not bad for, remember, 4 ohm load. That would be 125 watts. So, and that's at 20 kilohertz, and probably at 1 kilohertz, which is where they rate a lot of these things. Pretty close to its ratings. Okay, let's look at our square wave and see what kind of rise time we get. You can see there I'm maxed out on power, and my rise time is about 58 microseconds. So let's do the math. So looking at the numbers, we have about 4.9 volts per microsecond for our rise time, or our slew rate. Not great, because we like to see around 7. So again, that's going to be partially because of that the the choice that they have in op amps for the servo circuit. So it's going to slow things down. But it's acceptable. It's not bad. Okay, I hope you can see this all. So I have the THD meter set up. I'm directly across the speaker terminals. I am going into an 8 ohm dummy load, so this is real live distortion here. And let's start going up. So you can see, you know, you get around 20 volts or so, you start getting some distortion here and it starts breaking up. At lower power, it's still not very good. Yeah, the distortion figures kind of suck on this thing. Now, I don't think that's what this is supposed to be like, but that's what we're getting right now. It's just 0.5% to 1%, which to me is not very good. See, at low power, you're all right. So when we're looking, you know, where it starts getting out of hand is right about there at 7 volts, which is not that much really. And as I go up, it just gets worse and worse. So I don't know. Okay, so right before clipping, we're about 0.88% THD. And again, a little of that is, you know, the test leads and the, you know, the signal generator and so forth. And there's a possibility I could lower that a little bit by fiddling around with the output of the signal generator and things like that. But real world scenario, that's what this is getting. Could we clean that up a little bit? Well, probably by changing some lead dressing, by swapping out some components. Remember, I didn't replace any of the transistors in the front end or any of those sorts of things. Just did a quick recap on it. But that is what it is. Now, we also could probably fine-tune it by adjusting those DC offset voltages and so forth. But because at very low, let's cut this way down. See, at very low power, there is no, I mean, I don't see any kind of crossover distortion. We're at 0.011%. So this is definitely something that has to do with the amplitude, you know, as we're cranking up. So at very low listening levels, this is a very clean amplifier, but as you start driving a lot of power into it, that's where you start seeing distortion. Again, a little bit of that is my test setup. So, you know, it could be a little bit better by changing, you know, my speaker lead cabling and some things like that. Could make it a little bit better, but again, it is what it is. You've seen this test on so many other amps on my bench, and it just blows this test away, usually. So part of it is just, it's this amp. Okay, I have some music connected up to this, and the only thing, this amp is all done. The only problem that I could not fix, other than that little higher distortion that I'd be happy with, is the subsonic filter. If I turn this on, the right channel will trip the protect circuit because we get DC offset. I believe it has to do with the actual switch. This is one of those linked switches. So when I turn this, there's this cable. The switch is located back behind here, back in the corner, and I tried spraying it and cleaning it and all that, but when you move it over to the on position, which you would use this for like turntable rumble if you're listening to records, which most people don't use that, but if you were going to use that, I would have to troubleshoot it and fix it. If it's the switch, I can't get any more of those switches. They're unobtainium as far as I know. If it's something else on the equalization amplifier, well, that would require some very difficult troubleshooting that's not worth it to me. So I'm just going to leave that one alone. We're going to listen to a song called Bet On It by Silent Partner. It's a YouTube safe one, and I played this before a long time ago for some videos, but it's been a while. So I'm going to play that one. We're going to kind of demo this a little bit as best we can. Yeah, you're not hearing the amp, you're hearing the YouTube, and you can make the comments, but I already know that, and so do the rest of us, but a lot of you like to hear it, so I'm going to play it. That's going to be it then. I'm going to get this thing off the bench. Okay, so chances are I have a little bit extra distortion because I looked at the record level on the camera and noticed that it was hitting the maximum peak quite a bit. The dynamic power on this is actually pretty impressive because the actual instruments weren't even, halfway on the record level, but anytime the snare drum or the kick drum came in, it actually spiked the output. So there's a lot of dynamic power in this amp, which is good. That's a good thing. In my opinion, with my ears, for my personal preferences, I'm not real keen on this amp, and it's not because of that distortion. I've seen amps that had 1% distortion that sounded phenomenal. I think this is trying to mimic something like the Sansui AU-X1, and it misses the mark on it to me. I think there's other people who may like this amp. It's very, when I say kind of transparent, it's transparent in that I can't even say that it's transparent. It sounds too flat, if that makes sense. It just doesn't, even though it has good dynamic power, it sounds flat to me. I kind of like a little bit, I don't know, a little bit more of an inverted bell curve a little bit in my sound. I don't like it when you artificially put it in with the tone controls, but I don't know if that makes sense. It's kind of hard to put into words, but this amp is good. I could listen to it, but I think it would be a little bit fatiguing on the ears for me after a while. Part of that because of my hearing loss, part of it because of my taste, my preference of what I like in sound. Hope that kind of explains it a little bit. I don't want to discourage any of you or make you, any of you who have one of these and like it, to tell you that your amp stinks. It doesn't if you like it. Now what I will say is it does stink when it comes to working on. This is one of the worst amps I've ever serviced as far as serviceability goes. Very awkward, very hard to test things with power applied. Major amounts of disassembly, you know, desoldering things from boards and things just to get to them. So not my favorite amp to work on, I could tell you that. And I just think it's over-engineered. I think there's a lot of simpler solutions that could achieve the same results that they were looking for without 3 different transformers, without using you know, all of those current sources, all the voltage drops in the, you know, in the power supply here in the main. I think that kind of anything that you gain by having the dual power supply thing for the ripple, you probably lose in all the voltage drops that you put in place by having all those steering diodes in the power supply. So again, really don't know what they were. I think this was just, they wanted something different that they could market as saying it's different than everybody else. And they achieved that, I guess. But I think that's enough comment on this. I'll let you all decide for yourselves, but I hope those of you who were curious about what was inside these, how they work, hopefully you got a little picture of that. And we're going to move on to another project. So until then, I wish you all peace, joy, happiness, and good health in your lives, and we'll see you again real soon. Take care, everybody. Bye-bye.